Welcome back to another video. Let's jump right into the topic of chi-squared, t, and f distributions. The chi-squared distribution is a special case of the gamma distribution, where the scale parameter, denoted as lambda, is fixed at 1/2 and the shape parameter, denoted as r, takes specific values like 1/2, 1, 3/2, 2, and so on. This distribution plays a critical role in statistics, especially in hypothesis testing and confidence interval estimation. The chi-squared distribution is widely used in hypothesis testing. It is used in tests like the chi-squared test for variance. Confidence intervals. It helps to construct confidence intervals for variance or standard deviation in normal distributions. Model evaluation. In regression and analysis of variance, ANOVA, the chi-squared distribution is used to evaluate models. We will be discussing these topics in depth in the future. The mean of a chi-squared distribution is equal to the shape parameter, r. This means that if r is 2, the mean of the distribution is also 2. The variance of a chi-squared distribution is equal to 2 times the shape parameter, r. For instance, if r is 2, the variance would be 4. Here you can see how we can use Python to calculate a chi-squared CDF, PDF, and visualize it. We can use chi2 to model a continuous chi-squared distribution. In addition to using CDF function for retrieving probabilities, we can use PPF function for retrieving chi-squared values. Here are a few examples on how to find cumulative probabilities and chi-squared values. The t-distribution is a probability distribution that is similar in shape to the normal distribution. Both are symmetric and bell-shaped, which means they are centered around a mean value, and the probabilities decrease as you move further away from the mean in either direction. However, the t-distribution has a distinctive feature. It has heavier tails. Heavier tails mean that the t-distribution allows for a higher probability of values being far away from the mean compared to the normal distribution. In other words, extreme values, outliers, are more likely to occur in a t-distribution. This characteristic makes the t-distribution more accountable for smaller sample sizes or when there is uncertainty about the population variance. This makes t-distribution very practical in hypothesis testing, confidence intervals, and regression modeling. We will explore these in later discussions. Although the t-distribution is bell-shaped and symmetric, similar to the normal distribution, but its shape depends on its only parameter, the degrees of freedom. For smaller degrees of freedom, 1, 2, 3, the t-distribution has heavier tails as shown in the figure. As the degrees of freedom increase, the tails become thinner and the distribution becomes more concentrated around the mean. Ultimately, the shape of t-distribution approaches the normal distribution as the degree of freedom become very large. The mean of the t-distribution is 0, just like the standard normal distribution. This makes sense because the t-distribution is symmetric around its center, and the mean serves as the point of symmetry. The variance of the t-distribution depend on its degrees of freedom, nu, and is the formula for the variance in nu divided by nu min 2 for any nu greater than 2. As the degrees of freedom increase, the variance approaches 1, which is the variance of the standard normal distribution. Here you can see how we can use Python to calculate a t-CDF, PDF, and visualize it. We can use t to model a continuous t-distribution. In addition to using CDF function for retrieving probabilities, we can use PPF function for retrieving t-values. Here are a few examples on how to find cumulative probabilities and t-values. The f-distribution is defined as the distribution of the ratio of two independent chi-squared random variables, each divided by their respective degrees of freedom. The shape of the f-distribution depends on these two degrees of freedom. The f-distribution is right-skewed, meaning it is not symmetric. The skewness decreases as the degrees of freedom increase and approaches a normal-like shape. The f-distribution takes only non-negative values because it is a ratio of squared values. The f-distribution is critical because many statistical tests rely on comparing variances either between groups or between models. Its ability to handle ratios of variances makes it particularly suited for these tasks. It serves as the foundation for evaluating whether observed differences are statistically significant. We will further discuss these in the future. Here you can see how we can use Python to calculate a f-CDF, PDF, and visualize it. We can use F to model a continuous F distribution. In addition to using CDF function for retrieving probabilities, we can use PPF function for retrieving F values. Here are a few examples on how to find cumulative probabilities and F values. Thank you for your attention, and see you in the next video.